My name is Nicolás, it's Pablo. We are presenting a type inference algorithm we've made with help of Stephane and Ducasse. Let's just go to the next. Okay. First, I will talk about the objective of our work. We want to type to obtain type information for object-oriented dynamic languages. We're working in Pablo, but we want to extend it to other object-oriented languages. Our objective is not to type check a Faro program to determine if it's type safe or not. I think it wouldn't be possible, or it would make us to leave some programs out. We want to simply improve the tools of Pablo, feeding them with type information to improve refactorings, to improve code completion, suggestions, or code navigation, and help the programmer understand the code. So this poses some restrictions of what we are going to do. We want to work on real programs. We do not limit the programs you can write, and also on existing programs. And to improve tools, it has to work in an interactive time. So a person working on the Faro has to get type information as he types, or something like that, or every time he compiles a method, he has to work in that amount of time. And also we want to, this is kind of difficult restriction, we want to be able to type a library, not a whole program, because there's many works on typing Smalltalk start from a program without parameters. And that simplifies the program a bit, but it also limits us, and it doesn't allow to type a library which has a main method. So, these are some of our contribution. The algorithm is capable of coping with block closures and generic data types. It doesn't right now infer a generic data type from a collection, for example, but with some annotations we can describe that an ordered collection is a generic data type, so the rest of the program using that data type, it can take advantage of that information. It combines abstract and concrete types. So concrete types are multi-classed, and abstract type are sets of messages. And it's configurable and extensible, so we are going to continue proofing. It's a good base for making more experiments. And it's that was one of our requirements. It's a flaggable type system. It means that if you can take it out and everything continues to work and it won't bug. So, what's the problem about this? One of the most important, most difficult problems is that most type inference algorithms analyze how your data is used. And this is very difficult in object-oriented languages. For example, this little piece of code, I cannot say what method can be executed when I send the var message to this object, because I don't know what class is this object. And so the data flow and the control flow are intermixed in object-oriented languages. This makes it very difficult. And it is more difficult if you have to type this without knowing who is going to call you. If you start with a method without parameters, you can always know it or reduce it to the set of possibilities. But without, if you want to type check the Faro core, you cannot do that. So we have a strategy here that is to do an iterative algorithm. What does it mean? It runs very times over the same code, and it continues gathering information, and it always grows the information that we have. So how is this organized? this slide depicts the algorithm, the big picture of the algorithm. In not the following will be more interesting, I think. But we have to go through this to understand the others. So it is divided in a set of tasks. Each task gathers some specific information with some specific strategy, and there's a workflow that goes through the tasks and in seeing which outcome from the outcome of the preceding task, the task decides what is the next task to run. So this was in principle an idea to organize it with, because at some point the algorithm became too heavy for us and we couldn't understand what we are doing. So the idea to divide it in tasks works very well for us. But at making that, we also describe it's also extensible and configurable because we can reorganize the task in another ways in the workflow and allows for the proofs I was saying through. So it helps us learning, and we have very crazy ideas about proving some tasks and including fuzzy logic or something like that. But this is still work to do. So the most important task is the first one, which analyzes the code for a method, and it gathers constraints for each expression in the method. So for each expression, we create a type variable, and then we relate the type variables through subtype constraints. So each time we have an assignment, we say that the variable to be assigned has to be a subtype of the expression in the right-hand side. So the subtyping is not really not necessarily related to inheritance. So a subtype is a bigger set of types than a subtype in terms of concrete types. So it's a bigger set of classes. So each time we have one of these, an argument, a return statement, or an assignment, we relate two expressions that, through a subtype relationship. And also we generate receive message constraints that will give us the abstract type of an expression or a variable. After this we have some subtype relationships that will be giving us the concrete types, and the message sending will give us the abstract types, and we combine both types of information. So for each type variable, we gather all this information, the relationships, and we start to compute this kind of information. Minimal set of concrete types, which is a set of classes that we know that this variable it is possible to be the object referred by this variable will be can have instances of it, and then the set of messages that each expression or variable has to understand, or the object referred by the variable has to understand, and from this set of messages we can compute a maximal set of concrete types, a maximal set of classes, which are obviously the set of classes that understand all of these messages. And with these two sets we can go narrowing the set of possible types that the expression or variable has to be.
What if I have DNO tender?
Well, if you have a DNO, we can handle it. But this is still work to do. But my answer to that is that we want to improve, for example, the refactoring. So the refactor now refactors all if you want to rename a method, it proposes to rename all the methods with the same name. So if we can, in some way, restrict that set of methods, it doesn't have to be perfect. It has to be better. Okay.
That's why we are not trying to type check some programs, because your program handling DNL, it's working. It's not wrong.
Okay, what's next? So these are the tasks we are working now. The first one is the one I already described. Generates type variables and constraints for a method. Then we propagate a set of concrete types. When we have concrete types and a message sent, we can link it with a method, so we can relate the methods between each other or expression in different methods. Then we also can propagate the maximal set of concrete types, going through the subtype relationships in the opposite direction, and in this case, when we have message sent, we can compute a maximal concrete type. And in some cases, for example, when we have only a singleton maximal type, we can say, well, this is the only type possible, and we say this is the minimal concrete type. This is not an extensive list of tasks. We have thought of more tasks, but this set has worked, and we've been making experiments with it. And this here is the current workflow we are working with. The numbers refer to the numbers here, and the arrows are how the workflow decides which task to run next. So if it has more information, it goes back, and if it doesn't, when he runs the first task and it can gain more information, it goes through in that direction. So I'm running out of time, so I want to let Pablo speak. So this is the description of one of the tasks, maybe the most complex one, but I will go.
Okay. Yes. Well, when we start looking for an algorithm for typing Pharo programs, we got with the problem that we need to handle block closures, because they have a special meaning, and it's all over the program, all over the world in Pharo. Well, then we came up with this solution, having a special variable that has, it's kind of composite type variable. It has the information about the expression of the block, but also about its parameters and the return value of all the block, the expression of the block. So this new composite type variable can be used in the relationships as the other type variables. It started to work almost magically. But the idea is that when you evaluate a block or when you call to value, you know what type of the parameter is. So it is very nice. The other big issue that we have to work with is having generic type variables for collections, especially. We are handling it by type annotations. We are detecting some kinds of classes marked with messages related to collections. The idea is to add another task that can detect if a class is a generic class. It can be used as a task. Well, when a generic type is detected, another variable is splitted for the elements of this collection, and it's worked in the same way as the other type variables. Well, of course, the type variable, we are treating these variables in an invariant way. So, of course, a collection of A and a collection of B are different. Even with some operations, they don't have the same meaning. Okay, just a small example. We have integrated first stage of our tool into Pharo. The idea is to show the information, then we have to do something with this information. But here we have a small example. This is A nice example is a task, an object describing a task, and the task can have subtasks, and it's a recursive structure with using something like a composite pattern. And well, when we added we compute the information about all the information. We are getting information about the types. We are getting information about the instance variables, and also for each of the methods in the class, what are the parameters and the return value. We are getting information about every expression in the class, but only showing what we think are the more useful. Well. Running without time, the nice one to see is total cost, that is the recursive one. Well, we have it here, you can check the code there. And well, then, as you see here, we get information about the type parameter, the parameter of the block, also get the information about the collection. Yes, this is the set of the minimal set of types, and this is the message it receives. And also, well, it computes that the return of this is all small integer. It gets information from the sum and from the adding the also. Yes, you get the information because it can be float. Well,
no, but it could be a large integer.
yes, or any. Because
yes, we simplify the numbers model for now, because I think it is a kind of difficult part, and it wasn't so interesting. So
Right.
we simplified it and started for
It's really interesting for us and really difficult.
Yes.
Because if we get it
as
wrong,
we don't want
okay, but that's why I in part way excluded compiler optimization, because it has a very different set of requirements.
Right.
What you have to do is different.
Yes.
Right.
The objective is what is aiming us in choosing the decisions. What we are doing now is we are not seeing all the Faro image at once. We are taking some shorts. We are taking some goods in the with some predefined information. This predefined information is not in the language; it's outside. It's not like language annotation, but in the same way, gets some path in the analysis. If we are trying to analyze code, well, the conclusion is that we support recursive programs. You can check it. The type parameters. We can check or we can type parameters, instance variables, local variables, and also any expression in a program. Works on Faro programs without modifications because we don't need any annotation. The idea is to provide more information. If we don't have the information, we don't do nothing, but the tool is working. It's not requiring something from the user. And it's the way as we build it helps to increase new ideas and test some more new tasks and some crazy idea like using some kind of fuzzy logic or maybe heuristics or maybe guessing. I don't know, can be a way of performing this. Well, what we need to do or what we are going to do in the future? Well, the lack of metrics in our work is something that we are trying to attack. We like to compare us with other solutions, also in precision and in performance. We are not, we don't have clear measurements, but we have nice hopes. We are seeing some results that are really hopeful. Well, we want to integrate with Faro tools. The rename tool is one of our objectives. Well, the scalability and the performance of the solution is essential to be usable in a real development environment, and provide formal proofs of what we are saying. Also, we will like to expand the get away of these cuts in the analyzing path and explore all the faro image, perhaps getting more information and having it having it for the tools. One of the ideas is to have an iterative and incremental way, so we don't need to reanalyze all the image all the way. But we have to work on that. It's just an idea. Okay. Well, that's all. Questions?
So again, you mentioned about comparing with other works, but have you guys looked at Lex Spoon's?
Yes.
Yes.
Yes, we have.
Yes. Yes.
How
Yes.
do you compare this work with?
The main idea, the main difference with others idea is the objective we have. Some have another objective like compiler implementation or compiler optimization or program distribution, and some have the same objective as tools, making tools, improving tools. Well, we are comparing. The idea is start to comparing with these other tools. In Spoon.
Yeah, and a little your suggestion which probably you have thought of. Yeah, with an incremental analysis, it would be super cool if you can show possible types as I type instead of choosing a
Yes.
Yeah.
Yes. That's our aim. We want to make it show the user the most information, but we don't want to restrain it. If he or she want to catch DNU and do whatever, it will be nice.
So, how big is this can grow in memory?
Yeah.
We have to work on that.
Yes, we have to work.
I haven't measured it, but it can grow very fast. So that's why we want to segment that. So we cannot analyze the whole image at the same time because it will be unmanageable. So that's why it's an objective to be able to type a library. So type check a library, also get some types.
Introduce some heuristic to say, okay, it's enough. Let's stop analyzing and something like that.
Yes.
No,
No,
imagine if you had, a type signature for collections and a type signature for the numbers. Something that you could load, you wouldn't have to recompute until went through somebody altered.
The idea is to type some program and keep only the information. We discard all the intermediate information that we don't know. We are thinking different strategies of cutting down the whole tree of type variables and relations, and so we need just these pieces of information. But I don't know, checking or taking the right ones are not trivial. We have to think in a strategy to.
Are you introducing abstract type names or are you sticking to class names?
No, we don't put names on the types. The abstract type names are the abstract types do not have names. They are only set of messages.
Good. Yeah.
Okay.